Okay, welcome everyone. We'll continue our lecture on model reference adaptive control. In this lecture, we are going to design an output feedback controller. Of course, we are still using Lyapunov theorem for our design. So we are assuming that we have a plant where we have only access to the output Y and the input U. In order to do the design, we have first to introduce two concepts. The first concept is the concept of a minimum phase system, and second one is the concept of strictly positive real systems. Once we do this, we will move on and we will show how to use a Lyapunov based design to derive an output feedback model reference adaptive controller. So first, let's start by talking about minimum phase systems. If we consider a transfer function g of s, and we call that transfer function minimum phase if all the zeros of the transfer function are in the left hand side of the s-plane. So that means that we don't have any zeros in the unstable region of the s-plane or the right hand side of the s-plane. And these are two examples. The first example here, this is a system that has a zero at s equal 1. So this is called non-minimum phase system. While this system has a 0 at s equal -1, so this is a minimum phase system. Let's see why the label minimum phase or non-minimum phase is given to a certain transfer function. If you consider the transfer function in the frequency domain, replace s by j omega, then the first transfer function can be rewritten as j omega -1 over j omega plus 2. If you calculate the angle of that transfer function, it would be the angle of the numerator minus the angle of the denominator, and you will notice here that you will have similar sign for the two angles, which means that the absolute value of the resulting angle would be greater than the absolute value of any of the two angles of the numerator and denominator. So that means that the absolute value of the angle increases compared to the angle of the zero and the angle of the pole. This is for the non-minimum phase system. If you consider the second case where we have a minimum phase system, in that case you will find the angle of the numerator positive, the angle of the denominator negative, and the difference between the two angles would be smaller than the angle of the zero or the angle of the pole. So that's why it's called minimum phase system. The typical response of a non-minimum phase system in case of a step response would be like this. I'm assuming a positive step input. You will notice that here is in the initial response, the response moves in the opposite direction to that of the final or steady state value of the response. So this kind of response reflects non-minimum phase behavior. Okay, actually it's not necessarily that all non-minimum phase systems would have this kind of response, but most likely they would. And a physical example of a system which is non-minimum phase would be the level behavior of a boiler. If you imagine that you have a boiler and you keep applying heat to that boiler, then we expect actually the level to go down because of the evaporation process. But what happens is that initially you will find that if this is the initial level, you'll find that the level increases, and then after a while it decreases because of the evaporation. Now, what is the cause of the transient increase in the level? The reason actually is that some air bubbles are formed within the water. So the level increases for a while, and then after evaporation increases, you will find the level go down, as we can see here. So anyway, this is what's called non-minimum phase system, and as I said, a minimum phase system would be a system that has all its zeros in the left-hand side of the S-plane. So this is the first concept. The second concept is the concept of strictly positive real systems. And if you have a transfer function g of s, it is called SPR if and only if these conditions are satisfied. First, the transfer function has no poles in the right-hand side of the S-plane. So the transfer function is called to be strictly stable. It has no poles or zeros on the j omega axis. No poles or zeros on the j omega axis. And third, the real part of the expression for g of j omega, if you replace s by j omega and find the real part of the resulting expression, you will find that always non-negative. So if these three conditions are satisfied, we call the system strictly positive real. And simply you can plot the Nyquist plot of the given transfer function. If you find the entire plot in the right hand side of the complex plane, then that system would be strictly positive real. Otherwise, if part of the response is in the left hand side of the complex plane, we call that system non-SPR. And these are two examples that will illustrate the point. If we have a transfer function like this, 1 over s squared plus s plus 1, if you plot the Nyquist plot, you will find part of the Nyquist plot already in the left hand side. So this is not SPR. While if you have a transfer function like this one, and you plot the Nyquist plot, you'll find all the expression, the Nyquist plot in the right hand side of the complex plane. So this is an SPR system. Actually, in SPR systems, the relative degree, which is the difference between the degree of the denominator and the numerator, should be either 1 or 0. This is specific for SPR. So if you find a transfer function like the first one here with a relative degree 2, because the degree of the denominator is 2 and the degree of the numerator is 0, then you can say just by inspection that this is not an SPR system. Okay, if a system is SPR, then it satisfies actually what's called Kalman-Yakubovich lemma, and this lemma will be used in our analysis in the design of a model reference adaptive controller. So if we consider a linear time invariant system, and we assume that A and B are controllable, A and C observable, then the transfer function, the corresponding transfer function to this system, which is C times Si minus A inverse B, is called SPR if and only if it satisfies the following condition. If there exists positive definite matrix P and another positive definite matrix Q such that these two conditions are satisfied. A transpose P plus PA equals minus Q, and B transpose P equals C. A, B, and C are actually the representation of the LTI system. If these two conditions are satisfied, then we guarantee that the system is SPR. Next, we are going to consider the controller structure. So we are assuming a single input plant with single output. Now, in order to go for the design, we need actually to generate auxiliary states. This is similar to designing an observer. So we have here two blocks. They are auxiliary signal generators. And the function of the auxiliary signal generator is to generate auxiliary states omega 1 and omega 2, where the dimension of omega 1 is equal to dimension of omega 2 equals n minus 1, where n is the order of the plant. Once we generate these two auxiliary signals, we form the control law as some gains multiplied by y, omega 2, omega 1, and r. So we can write an expression for the control signal as k times r, then theta 1 transposed times omega 1, and theta 2 transposed times omega 2, and finally again theta naught times y, which is here. So we can put this control signal in the form of a row vector times a column vector. I'm going to call that row vector theta transpose and the column vector omega. Our objective is to design theta. I'm going to assume that the plant is minimum phase, and we are going to give the transfer function of the plant the symbol WP, while the reference model I'm going to refer to it by a transfer function WM, and I'm assuming that transfer function to be strictly positive real, and that means that the difference between the number of poles and zeros should be either 1 or 0. And of course, the transfer function that refers to the reference model would relate the output, the desired output ym, to the reference signal r, while the transfer function that represents the plant relates the output of the plant, the true output of the plant, to the input signal u. As I said, the degrees of the auxiliary signal generated would be the degree of the plant minus 1, and assuming this to be n. Now, if we know the transfer function of the plant WP, we would be able to select theta so that the closed loop system would have a transfer function similar to Wm. In that case, I'm going to refer to the control law that achieves this relation as U star. So U star here refers to values k star, theta 1 star, theta 2 star, and theta naught star, which would be selected if we were to know the actual system, so that the relation between the input and the output would be exactly as the relation between the reference model output and the reference signal. Now, this line summarizes what I said, that if you have U star as an input to the plant, then this would give you a relation similar to the relation between the output of the reference model and the reference signal. I can put that in a block diagram. This is similar to the block diagram that we have shown before, except that I replaced k by k star, theta 1 by theta 1 star, theta 2 by theta 2 star, theta naught by theta naught star. And in that case, I have here theta naught star times y. Here I have, this is W2, so this would be theta 2 star times W2. Here, this would be theta 1 star times W1. And they are all summed together, plus this signal, which is k node r. So the result would be U star here. And the transfer function that relates y to r in that case would be the model reference transfer function, and in that case y would be equal to ym. So this is the ideal controller that I would use if the transfer function of the plant were known. Now, we don't know the transfer function of the plant. We cannot select theta to be equal to theta star. So in general, the control signal that would be applied is just theta transpose times omega. And the difference between the used value of theta and the correct values theta star, this would be the parameter errors phi. So in that case, I can write u as phi transpose plus theta star transpose times omega. This comes from substituting for theta in this equation by phi plus theta star. I can write this further as phi transpose omega, the error in the parameters times omega, plus the correct values or the true values of theta transpose times omega. And I can then redraw the block diagram similar to what I did before, except here I have an extra input which represents phi transpose omega, this term in the control signal. So in that case, the output is y in general. It's not necessarily the output of the reference model. However, I'm representing that block diagram in terms of k star, theta 1 star, theta 2 star, and theta node star. Now what I'm going to do next is to move this signal from its position here to be behind the block k star. If I do that, then I have to actually divide by k star. So the resulting block diagram would be like this. As you can see here, we have moved this block behind k star, so I just divided by k star here. But the purpose of that is that the resulting block diagram here would be just the reference model transfer function. As if you compare this block within the red frame with the omega m, you will find them identical because I have k star, theta 1 star, theta 2 star, and theta node star in the all the branches. So I can then write y as omega m, the transfer function omega m, with inputs which is the summation r plus phi transpose omega divided by k star, as I did here. And since Wm, the transfer function of the reference model, is a linear operator, then the output due to the two inputs would be the summation of the output due to each input individually. So I can write this as output due to r and another output due to phi transpose omega divided by k star, and this would be the total output. But since the first term has a transfer function equal to the reference model and an input which is equal to the reference or the set point, then the output of that term would be just the desired output ym. Once I do that, I can write y minus ym as an error signal. I call it E1, and then I will have at the right hand side the transfer function or the operator that represents the transfer function of the reference model with input equal to phi transpose omega divided by k star. So now we have managed to find an output error equation that can be used later on within our Lyapunov design to derive the adaptation equations and show that v dot is negative semi-definite. Remember, the reference model is strictly positive real. In that case, I can put this equation, which is an input-output equation, I can put it in the state space form. So I will choose a state variable vector E, where E is composed of E1, E1 dot, and so on, the derivatives of E1. AM would be in the controllable form, and some gain matrix BM, and the C vector would be 1 and then zeros. If you multiply that by the vector E, you will get E1. So this state space representation is corresponding to the input-output relation that represents the relation between the error and the input phi transpose omega divided by k star. Now, I can assume a candidate Lyapunov function as a quadratic term in E and quadratic term in phi as usual. P is positive definite, gamma is positive definite. And then I take the derivative, so that would be E transpose P E dot plus E dot transpose PE plus twice phi transpose gamma to the minus 1 phi dot. We have explained in the previous piece of the lecture why this is twice phi transpose gamma to the minus 1 phi dot. The same argument applies. And then I will collect together terms that contain E and terms that contain phi. Now, first I have to substitute for E dot. So this is E dot from its state space representation, and this is E dot transpose. Collect together these two terms here. So that would be E transpose P AM plus AM transpose P times E. And then I multiply E transpose P by BM phi transpose omega divided by K star. So this is the first element from here. And then the second term here would be this multiplication times PE, but this is a transposed term. However, phi transpose omega, as we mentioned before, is a scalar, so I can just take it outside, as I did here. And then I take only the transpose of BM, so this BM transpose times P times E. Then the last term, 2 phi transpose gamma minus 1 phi dot. Now, from the Kalman-Yakubovich lemma, we can replace PAM plus AM transpose B by minus Q, where Q is positive definite. So that's what I did here. This is also comes from the Lyapunov equation, since AM is a stable matrix. And then these two terms, I notice that this is a scalar and this is another scalar. If I take the transpose of a scalar, it remains the same scalar. So I will take the transpose of the first element here. That would give me BM transpose PE. And then these two terms will be similar. So that would result this summation. If we look here, we will notice that we have the product BM transpose times P, and again from Kalman-Yakubovich lemma, this would be just C transpose, but C is 1 and then zeros, and E is a column vector. The first element in E is E1, then E1 dot, and so on. So the product of C transpose times E, that will give me E1. So that's what I have written here, that BM transpose times B is C transpose, and the multiplication of C transpose times E is E1. And we know that V dot has this term which is negative, and the other two terms, the summation of the other two terms have indeterminate sign, so we put that equal to 0. So the result would be this equation. Now once I do that, I can write an expression for phi dot, and this is minus K star gamma E1 omega. Now I know that phi is the difference between the parameters that I'm going to use in the controller and the parameters that I would use if I know the plant transfer function. Theta star is constant. So if you take the derivative, that would be just theta dot. And the multiplication of K star times gamma, that would be another constant matrix gamma bar. Of course, in that case, I have to know the sign of k star, and that implies that I should actually know the sign of the original system gain. So that will lead to theta dot equals minus gamma bar E1 times omega, and gamma bar is normally a diagonal matrix, gamma 1 up to gamma n, and these are the adaptation gains. So this way I can implement the proposed control. Now it's left to explain how to design the auxiliary signal generator. Now the structure of the auxiliary signal generator, I'm going to assume a transfer function of order n-1, and the denominators of both auxiliary signal generators will be similar. The difference will appear here in the numerator, the C and the D parameters. I can put any of them in the controllable form, so I will have here the identity matrix of dimension n-2 by n-2, and then I have here the coefficients of the characteristic equation of any of them. They are similar. Then this is the B vector, and this is the C vector. Now the C vector will be the coefficients of the numerator. So in case of the first auxiliary signal generator, these coefficients will be the C parameters, while in the second it will be D. And that's what we called earlier theta 1 and theta 2. So this is the structure of the auxiliary signal generator. We select the zeros of the reference model as the eigen values of lambda 1, and then we use theta 1 transpose and theta 2 transpose as estimated from the adaptation equation to form the control law. So this summarizes the design of an output feedback model reference adaptive control based on transfer function approach. Actually, beyond the scope of our lectures, we could also design a model reference adaptive controller in case of a non-SPR reference model, but I will leave that up to you to read if you like. So thank you.